Light particles and matter waves. Physics 12, Clips of the Day. Minute of Physics on Wave-Particle Duality. http://www.youtube.com/watch v=q_h4iops http://www.youtube.com/watch v=_ev2im8. And the story continues. After the verification of the photoelectric effect, physicists started to ask more questions about the extent to which photons resemble particles of matter. Lead to questions about momentum and collisions of massless particles. Would the law of conservation of momentum hold? How can you determine the momentum of a massless particle? Compton 1923 used highly energetic photons from X-rays, high-frequency waves. He collided X-ray photons with and electrons. Discover the Compton effect. http://www.kcvs.ca/sites/projects/physics.html. Compton effect. When a high-energy X-ray photon collides with a free electron, it gives some of its energy to the electron and lower-energy photon scatters off the electron. Electron starts at rest. Following the collision, the photon is scattered at an angle as is the electron. Since the photon has less energy than the incident photon, it must have a lower frequency. Compton effect. Much like the photoelectric effect, Compton also used the particle theory to explain his results. Since we know that in a collision momentum must be conserved and the scattered electron has a momentum, the incident photon must also have momentum. This leads to the equation. How can a particle with no mass have momentum? Flashback E=mc2. So X-rays with energy E have a mass equivalence of E/c2, momentum of a photon. Example. Calculate the momentum of a photon of light that is a frequency of 5.09 by 1014 Hz. Implications. These collisions obeyed all the laws for collision between two masses. Compton's analysis supported the particle theory of light. Photons have a discrete energy and value for momentum. Compton won the Nobel Prize in 1927 for his work. What? We've seen light acting as a particle. But matter acting like a wave? De Broglie, pronounced De Broglie, proposed that electrons, too, have a wave nature and a wavelength, and that all material objects have a wave nature, matter waves. De Broglie determined the wavelength of matter waves using the following equation. Matter waves determine the wavelength of the following. You traveling in a car, 1,400 kilograms, at 100 kilometers per hour. An electron, 9.11 by 1031 kilograms, orbiting the nucleus at 9c. Are either of these wavelengths significant? Planck's constant, h, has such an extremely small value that the wavelength associated with any ordinary object is far too small to be experimentally detected. Verifying matter waves. In order to demonstrate that matter, like electrons, have wave-like behavior, it must be possible to show that they will have interference patterns. Von Laue and Bragg developed an X-ray diffraction technique that displays these patterns. Wave-particle duality. Within 30 years of Planck's presentation of quantization, the particle nature of light and wave-like behavior of subatomic particles had been accepted. Matter has a dual nature, but only subatomic particles have a small enough mass and thus a large enough wavelength to exhibit their wavelength properties.